last time, haha, which I know you guys aren't physically here for last time, but I asked you to watch the video, and hopefully you did. So we did a very non-comprehensive, it was not meant to touch all bases of inverse functions, what they are, when they exist, and we also went into how to find the derivative of an inverse function, which we found was, if you have a differentiable function, you want to find the derivative of its inverse. If it exists, it turns out that you can find its derivative via this formula. It's 1 over the derivative of the original function evaluated at the inverse at the point that you care about. So that was a very important function, a very important formula, and that is something that you should have memorized as well. And we'll talk about why this formula is important, because again, you might wonder, why do we even need this if we know how to find inverse functions? But we'll get to that. We also derived 2 other important formulas that I expect you guys to know at this point. The derivative of the sine inverse functions. You should be aware that another way to talk about this or write this down is called arcsine, because the -1 power sometimes means other things, right? It usually means 1 over. Turns out when it's talking about inverse function, it means something else. That's just a notation. But we can differentiate this function by doing this, and we actually derive this formula, 1 over 1 minus x squared. And we also looked at the derivative of the tangent inverse function, which we might call arctangent. That was 1 over 1 plus x squared. So we derived those 2. It is worth mentioning that every time I give you a formula like that, you should immediately start thinking of the chain rule version of the formula, because that generalizes it a little bit. So if you were to remember something, I'd say remember this. To differentiate sine inverse of u, that is going to be u prime divided by the radical of 1 minus u squared. And of course, we're assuming that the domain works here, and you should know that your u for this to work needs to be strictly between -1 and 1. So that's the chain rule version of this guy. So u can be any function of x here, and that's how we find the derivative of the sine inverse of that expression. Similarly, we can have the derivative of tan inverse of some general function. That would simply be u prime over 1 plus u squared. And there's no restriction on the u here. That'll work for all real inputs of u. And so those are the chain rule versions. Just an FYI, we'll probably talk about this in Calc 2 a little more. You do know the derivatives of the other ones. So we can talk about the cosine inverse, we can talk about the cotangent inverse, we can talk about the secant inverse, we can talk about the cosecant inverse. And it turns out that a lot of these are similar. The derivative of the cosine inverse function, quite similar to the derivatives of the regular trig functions, is actually just the negative of that guy. So this is just -1 over a radical of 1 minus x squared. And again, your x has to be strictly between -1 and 1. The cotangent inverse happens to be the negative of the tangent inverse. This would be -1 over 1 plus x squared. The secant, again, you'd use a similar method to derive those. This one would be 1 over absolute value of x squared root of x squared minus 1, and this would be the negative of that. And these 2 work for all x that are not between -1 and 1 inclusive. So it works outside of that range. So you have to be strictly larger than 1 or strictly less than -1. Now, I don't expect you to know this. You're not responsible for remembering this or whatever. But these 2 I do expect you to know, the sine inverse and the tangent inverse functions. They show up pretty often, and even in Calc 2, usually a professor will only put these two guys to be mean, really. You're really expected to know the top 4, and if these guys ever show up, you can look it up in the textbook. Usually you won't be tested on it, but don't quote me on that. It depends on how your Calc 2 professor will treat this. But knowing these two guys are important, these two guys you'll notice are just the negatives of those guys, so they usually don't test those. But the tangent inverse is is the typical tangent inverse, sine inverse. So if your teacher wants to test you how you deal with inverse trig functions that have some sort of restricted domain, he's going to give you this. If he wants to test you with some sort of trig function that is defined on the entire real line, he'll probably test you with this. So that's that. But ultimately the main result was this one, and we used this to figure out all of that. Okay, so that's kind of where we ended up with last time. And we did a few examples. These two were actually the first 2 examples we did, and we had a third example. Now the third example is going to illustrate why this formula was important in the first place. So example 1, part C, asked us to find, let me write it down here, we're just going to jump right back into it. Our function was this guy. And you needed to find the derivative at the end of the inverse evaluated at the point 2. Did anyone actually attempt this, try to figure out how to do it?
I did, but I don't know if I did it right.
Okay, sure. Tell me what you tried.
Well, I used the equation, so 1 over.
Right, so we know that the derivative of the inverse evaluated at 2 is going to be 1 over f prime of f inverse at 2. Ultimately, that's what we want to figure out. Okay, so what did you do with that?
So I put the derivative on the bottom, so I got 1 over.
Well, what was the derivative?
5x to the 4th minus 3x squared plus 2.
Okay.
And then you're gonna multiply that by the.
Well, you're not multiplying, you're plugging it in.
Yeah, you're plugging in. Oh yeah, that's where I went wrong.
Oh, you actually multiplied?
Yeah.
Yeah, no, this was a composite function.
Yeah.
So it's the derivative evaluated at the inverse of 2. So we know the derivative part of the formula. What is f inverse of 2? How would you go about finding f inverse of 2? What does f inverse of 2 mean?
Is that when you sorry, you plug in 2 for x or only 1?
2 for x where?
Isn't that that's an explanation?
Well, no, because that would be f of 2. If I just plug in 2 for x here, I'm finding f of 2. I want to find f inverse of 2. So I want to find what is the output from the inverse function. How would you go about doing that? In the grand scheme of things, what does this 2 represent?
X.
X as in which x?
The x of the inverse function.
Okay, so let's think about this. Let's look at a diagram. Let's say f is going here, and we know the inverse is going to reverse that. That was the idea. where would the 2 live?
Codomain.
In the codomain. So the 2 would be over here. Okay? So where did that 2 come from?
Is the output of
It's the output of
Of the domain.
some acts of
the original function, right? That 2 is the output of this, right? So we had something over here that when we plugged it into f of x gave us the value 2. Okay? And we kind of know this about inverse functions, that the codomain and the domains actually switch roles. The output of the original is the input of the inverse and vice versa, right? So when you see that f inverse of 2, the fact that it's an input in the inverse function means it's actually an output of the original function. So what you need to do is if you set f inverse of 2 equals x, what that actually means is that you want to find the x value such that the output of the original was 2. Now, how do you go about figuring out where the output of the original was 2? Okay, so we have f of x equals 2. That would mean what? Well, that means x to the 5th minus x cubed plus 2x is equal to 2. Can you solve that for x? Can you guess what x would be? Huh? X equals 1. And here's where you'd write something like by inspection. Now you didn't actually solve anything, but you can kind of see that 1 minus 1 plus 2 would actually give you 2 if you plug in x equals. Yes?
So we can do that on exams, so just like this.
Yes, you can say by inspection. Now, in this particular case, you can actually solve it. If you bring the 2 over, you can do a factor by grouping maneuver and you can actually find what the x value is. In general, though, that's going to be pretty difficult. Most of the time in a question like this, you are going to want to find the x by inspection. And that's okay for a couple of reasons. And it goes into talking about why this formula is important in the first place. So we mentioned when we were doing implicit differentiation, and we grappled with the question where it's like, why do we need implicit differentiation? Why can't we just solve for the y and then differentiate it the old way? And the problem with that was sometimes you can't solve for the y. Sometimes it's actually impossible to work out the reverse function. And that is an issue here. The reason why this formula is important to us is that sometimes finding the inverse function in general is not really possible. So you might remember from pre-calc that if you want to find an inverse function, you would set this equal to y. What you do is you switch x and y and you solve for y, right? This is a 5th degree polynomial. There is no general way to solve for that in terms of a formula. Kind of goes by a case-by-case basis. And some specific numbers might work out, but if I put any other random number here, like a 3, that's now kind of impossible to solve, right? So a lot of the times you'll be given a problem of this nature. The problem that you're going to be given is kind of going to be one where you can't really solve it by hand. This one is an exception, but usually not. And what you can do is you can kind of just guess and check some really easy numbers. And in this case, 1 actually worked out. Now, it's fine to know that 1 is going to be the answer because, as I mentioned in the last class, which you guys were half here, the fact that for a function to have an inverse, it has to be 1 to 1. So I know once I find one x value that works, that's actually the only x value that works. I know that's the answer, right? And that's the only answer there could be because it had to be 1 to 1 to get this inverse. So there's only one guy who's going to have an output of 2. And if I can just see that guy, we say by inspection, then I don't have to worry about it. And so the idea is the following. Sometimes you have a function, but you're concerned about its inverse, and you want to examine its inverse under calculus. But you can't find the inverse in general. You can't really switch x and y and solve for y. It's impossible to do that. And so what you would do is, again, you kind of do it on a point-by-point basis. For very isolated specific points, you can figure out the answer for that particular point, or you can approximate that using numerical analysis of some sort. And then you can actually find the derivative on a point-by-point basis for the points that you care about. But there would be no general answer. Okay? So that's why this formula is pretty important. We can't always find what the inverse is. Sometimes it's actually pretty impossible. And you get lucky sometimes, but a lot of times, most of the times, you don't. And so you kind of do this thing, and you try to approximate a solution to whatever function you have here. But in a Calc 1 class, we're going to give you something where, even if it's impossible to solve for the x value, it's kind of going to be obvious, quote unquote, what that x value has to be. So it turns out here that our x value would have to be 1 to output 2, which means that our f inverse of 2 is 1. So this, ultimately what this gives us is that the derivative of the inverse of 2 is going to be 1 over f prime of the number 1. Now f prime we found is this guy, so all we have to do is plug in 1 into this guy. Plug in x equals 1, we're going to get 5, 7, minus 3, that's 4. So the slope of the inverse function, when the inverse function's input is 2, is a quarter. So that's the answer. We also had some other examples. Any questions on this? So you start out with the formula. The derivative part of the original is something that you should be able to find pretty easily at this point. And the hard part of this is figuring out the inverse at a particular value. You just have to remember that the input in an inverse function is just the output of the original function. So using that, you can set up an equation. Sometimes you can solve this equation nicely. But a lot of times it's going to be impossible to solve this equation, which is why we needed this formula in the first place. And so the equation, whatever it is going to be something that usually a very nice value of x is going to give you the answer. And so you kind of see it by inspection, and you'd write this down. X equals 1 by inspection. That's basically a way of saying, oh, I just saw it. And then once you do that, you just plug it into the formula, and you can figure out the derivative. Let's do some finding derivatives. That was the second example. Just getting used to the new formulas that we got, the trig formulas. So in our second example, we wanted to find y prime. So, you guys weren't here, so I'm gonna do something uncharacteristic and kind of help you out here. Just remember that this guy is that, and this guy is that. You can insert, put the chain over, insert. Okay, what's the first one?
Negative 2x over the square root of 1 minus x squared, quantity squared.
Can do that. You can even sort of simplify it here a little bit, but I probably wouldn't worry about it. That's pretty much good enough. So this is your u. So in this case, this guy here is your u. So this guy here is going to be u prime, and you plug in your u here. And that's basically it. Nothing really to see here, just making sure we go through some examples. What about this one?
$48x cubed over 1 plus 9x to the 8th.
So where the 48 comes from? Well, there's a 4 here times, now we're going to apply the rule here, so it's the derivative of this, which is going to be 12x cubed over 1 plus that thing squared. So I just put in the 3x to the 4th here. And then the 4 times the 12 gives us the 48. That's your answer there. What about C?
This one's product rule, I think.
Product rule.
So
One function times another one. Right, those rules that we derived in the early days of derivatives, they will always apply forever. It doesn't matter if you're talking about new functions, oh, this is an inverse function. Doesn't matter, product rule still applies, quotient rule still applies, chain rule still applies. Can't forget the old rules just because we're learning new ones. That's very important. So yes, we have two functions here multiplying by each other, so we have to go through a product rule. So what would that look like here?
2x times sine inverse of 4x plus x squared plus 1 plus times 4 over the square root of 1 minus 16x squared.
1 minus 4x all squared. And don't really have any common terms here to pull out or anything. And you can leave it like that, or just make sure that this is 16x squared, because both the 4 and the x should be squared. Okay. What about this guy?
This one's in, go ahead.
You want to try it?
Honestly, wouldn't you use like the, I don't know, like the correct, I guess. Like you don't distribute the sign because it isn't distributed across. the-
Right.
But like it does, like it would be sine x cosine y plus cosine x sine y.
No, that's
Like
for
it goes-
sine.
that's
This is
for-
sine inverse.
Yeah.
You don't
Oh,
have
never
that
mind.
formula for
Never mind.
the inverse function.
This one's implicit.
It's implicit, because we have x's and y's jumbled together. I don't just have y equals some function with only x's in it. So I have to do implicit differentiation. So what does that mean? How do you differentiate this guy?
1 over, oh, okay, sorry, I have it separated. 1 plus y prime over
1 plus y prime over,
the square root of 1 minus x plus y squared.
right? Again, it's the derivative of the inside over the radical of 1 minus the inside squared. Now the derivative of the inside is just derivative of x is 1, derivative of y is y prime. Plus derivative of y,
Y prime.
prime, derivative of x squared, 2x. And I think that's the last example, so let's continue. So here, this guy just splits up into 1 over that plus y prime over that. Plus y prime plus 2x. So now, as always, we're going to isolate the y primes. And so, the y prime is going to be that guy. Which I could rewrite a little bit nicer. I just multiply and divide this by 1 minus x plus y whole squared. Any questions on this? So you're applying it just like any other derivative rules, not forgetting things like the product rule still exist. Things like implicit differentiation still exist. Let us move on. So that's all I really expect you guys to know about inverse functions, being able to solve these kinds of problems. So the kinds of problems that are important for us are like all the problems in example 2. So you see how in test 1 I asked you a bunch of derivatives for one of the problems. In like test 2 and the final, within that group of derivatives, I'll probably throw in one with, you need an inverse trig function in there. As well as example 1 part C is another very typical problem that I would ask on a test or a quiz. And I'd probably ask one where you can't actually solve for the inverse and do it the other way, so you should know how to do it this way by inspection. that being said, for the remainder of the time, I want to talk about another application of derivatives. We're going to be stuck on the first derivative for a while. We'll start talking about higher derivatives later. But this particular application is called related rates. So this is section 2.8 in your textbook, not that we've been keeping track, but it's a very word problem heavy section, so I'm not going to be writing out these examples on the board. Oh, you already printed that out? That's great. So instead I gave you handouts. So this handout is pretty comprehensive in the sense of what we'll be learning and doing. So the first and the top part of the page actually tells you about how this process works. So we can kind of just read through it quickly. And then the rest of the page and a half is just some examples, right? So this is typically what a related rates problem examples would look like, and we'll talk a little bit more about that. But this is related rates. It's one of those more qualitative applications of a derivative. So remember that one of the main goals of the derivative was to solve the rate problem. We wanted to figure out how fast something is moving. It turns out, ever so often, that quantities are sometimes related to each other. One might depend on another. So as one quantity is moving, it causes something to happen to another quantity, right? So we can have quantities that are related, and maybe we can even come up with an equation that relates these quantities. And so now, let's say you have all the information about one of these quantities, right? I know what it currently is, I know how fast it's moving, etc. But you want to find out all that information for the other quantity. You say you're doing a related rates problem. That's the problem, okay? So sometimes you have related quantities, and it turns out that once quantities are related, we'll usually do two, but in general this can be expressed in one. Given two or more related quantities, and we're assuming we can find an equation that relates them. So we might have two quantities that are related. It turns out that we can actually use this. We can find the relationship between their rates. And that's by doing something pretty simple, just differentiating the equation that you had before. So I have two quantities that might depend on each other, they affect each other. And assuming that we can come up with an equation that tells us how the relationship between these two quantities are related, it turns out that we can figure out how their rates of change are related by simply differentiating that original equation. So if I know about the rates of change of one, I can figure out the rates of change of the other one, right? And the nice thing about this is sometimes, depending on what you're measuring, it might be easier to figure out the rates of change of one than the other, but once you figure out that guy, you can kind of use this equation that you came up with to figure out any rates of change of the other guy. So when quantities are related, turns out their rates of change are also related simply by differentiating that relationship equation. And this idea, this process of figuring out rates of related quantities are called related rates. That's why they're called that. And so there's a process that we go through. Some key takeaways here. Whenever you're doing a related rates problem, the independent variable is always time. At least it will be for us. So we're talking about rates in the real sense here. We're always talking about how something is changing over time. Okay? Which that means that the differentiation that you're doing here is always going to be with respect to time, with respect to t, which means that if you have any other variables in play, you are going to have to apply implicit differentiation. You're going to have to use the chain rule. And because t is the only thing that when you differentiate it, won't have some kind of chain rule reaction. Right? Everything else will. Right? So the independent variable is always going to be time, which will often be denoted by t. Okay? So that's one other thing. For the second part of the course, we are going to be doing a lot of word problems. It's not going to be straightforward calculations like in test 1. So you might have several word problems on a single test. So you should know how to recognize something is a problem is a related rates problem. Well, that is when you're reading a word problem and you kind of realize that this is the situation you find yourself in. You're given a description of a relationship. Between quantities. And are told all but one of the rates. Or you can reliably figure out all but one of the rates. And then the question asks you, you're asked to figure out another rate. Whenever you see a word problem like that, it is a related rates problem, right? So the kind of really broad, general template for such a problem is, hey, these two things are related in this way. This one is moving this fast. How fast is that one moving? It's kind of a related rates problem in a nutshell. That's kind of how it's going to be. So now, you're going to be given a description, can come in all sorts of shapes and sizes. Oftentimes, you are the one who will have to figure out the relationship. It will often be one that you can figure out through some sort of geometrical relationship. So basically they're going to describe a situation that you can kind of sketch something to see what's going on, and it should be some familiar geometric shape usually, and you can actually use equations that you know about these shapes to figure out the relationship. And you're going to be told how fast a bunch of things are moving, and you're going to be asked how fast is some other thing moving. And this is a related rates problem. Okay, that will distinguish it from the other word problems we'll be talking about. The next big word problem situation is going to be optimization. So that's basically the idea. Here I mentioned, and we're going to talk about this. This is pretty much the process to go through to solve any related rates problem. This will work on any related rates problem I give you in this class. Once you know these 6 steps and really understand these 6 steps, a related rates problem should not be an issue for you. I do remind you of some of the relationships that you need to remember. So you need to remember things like areas of rectangles, triangles, circles, volumes of cylinders, cubes, Pythagoras' theorem, SOHCAHTOA. All these things actually come into play a lot. And a lot of the times we're testing you on one of these guys. Okay. So here, these are some word problems that are examples of what a related rates problem might look like. And you'll realize that they would all actually follow this pattern. So now, once you're reading a word problem that you want to solve, You figure out it's a related rates problem, you might now wonder, how would I solve this problem? Well, there is a 6-step process by which you will solve every single related rates problem. You will always go through these 6 steps. You will always tend to go pretty much in order. There are times when you might skip a step or two, and I'll talk about that. Well, we can actually read through this before we actually do an example. We'll read through this and then we'll do an easy example. Probably example 2 is easier than example 1, but we might start with example 1. Okay? So, the method of related rates. So this is the process that you go through to solve one problem like this. Okay? So they're going to talk about, okay, some things are related this way, this is how fast one of them is moving, figure out how fast the other one is moving. And you're like, oh, that's related rates. So you immediately go through these 6 steps. Step 1, which is kind of step 0, you need to read the problem carefully. Okay? So things are going to be described to you, and you have to read it very carefully, because oftentimes you're going to need to put those words into a picture. Right? So something's going to be described, and you need to figure out, okay, let me really understand what's going on in this situation, because I'm going to need to figure out a way to diagram the situation somehow. So you have to really pay attention as to what is going on. You also need to pay attention as to what things are changing. It turns out things won't always be changing. Like problem 3 is a good example of that. So yeah, read the problem carefully. Okay, so you kind of browse through it, realize it's a related rates problem. Now you go back over the problem and you really read it carefully to try to set up something. Step 2 is, if possible or necessary, you need to sketch a diagram of the situation. Okay, and it's very important that you label this diagram intelligently, right? Which is what, going back to step 1. So you need to label the things that are changing with variables, right? So things might be changing and some things might not, right? You need to label anything that is not changing with a constant, okay? Because once you're taking derivatives, you need to know when a derivative is going to 0, for example, and not think there is some extra quantity out there that you need to figure out. So you need to draw a diagram of the situation, label it very carefully. If something is changing, you label it with a variable. If something's not changing, you label it with a constant. Okay. 3, you are going to write down the information you're given about the rates, right? So like I said, you are going to be told how fast some things are changing. Write that down. You also should write down what you intend to find. You say, this is what I know, this is what I want to find. It keeps you kind of focused. Because usually there's a lot of variables in play, and you don't want to get lost. A lot of times you could get lost if the problem is sufficiently complicated. So you tell yourself where you are, tell yourself your goal. 4 is to finally you're going to set up an equation that describes the situation. Okay? So based on the diagram that you drew, you need to come up with an equation. So if your diagram is ends up being a right triangle, you're going to start thinking about maybe SOHCAHTOA, maybe Pythagoras' theorem, maybe that's a relationship. Okay? So you're going to come up with a relationship. This also talks about when step 2 might not be necessary. So usually you only come up with a diagram in order to come up with a relationship. Sometimes the relationship is actually given to you in the problem, and so you don't need the diagram. You can kind of skip over step 2 and move on. Okay. Once you come up with a relationship, you are now in step 5. You are going to actually differentiate implicitly with respect to time. It will always be with respect to time. T will always be the independent variable. Once you do that, you'll get a new equation, now with the rates of change in play, because the chain rule will kick in, and you'll see the derivatives pop out. You will know the values of pretty much all the derivatives, and you need to find the values of one of the other ones. And so step 6, you're going to plug in your knowns, all those guys you stated way back in step 3. You're going to plug in all those values and solve for the value you want. At that point, it's an algebra problem. Fair warning here, sometimes all the quantities that you need won't be given to you, but you can use the relationship in step 4 to figure out anything that is not given. That will usually be the case. So if you go here and you realize you have more than one unknowns, chances are you need to go back to step 4, figure out what you don't currently know, and then go back to step 6 and plug it in. And by the time you get through step 6, that's going to be the end of the problem. Okay? So a 6-step process, read carefully so you can draw a diagram that describes the situation. Write down what you know, what you want to find, and set up an equation that describes the situation, often based on your diagram. If you're given the equation, you do not need the diagram. Once you set up the equation, differentiate it implicitly with respect to t, and solve for your unknowns that you need to solve for from the problem that will be described. So let's actually get through one of these. I guess we'll go through more because we have about 5 minutes left. Or actually, because I know this clock isn't exactly right. Let's do example 1. A right circular cylinder undergoes expansion. The radius is increasing at 1 meter per second. The height is increasing at 2 meters per second. How fast is the volume changing when the radius is 1 and the height is 3? So step 1 here, still use the problem carefully. Step 2 here, to set up a diagram. This is a right circular cylinder. It tells me the radius is changing, therefore I will call that R. It tells me the height is changing, I will call that H. Now that diagram is supposed to start conjuring up familiar formulas from high school geometry, I think. You would then move on to step 3. So step 2 was diagram. Step 3, right now what do we know and what do we want? So far, I know the radius is increasing at 1. This means the rate of change of r with respect to t is positive 1 because it's increasing. And its height is increasing at the rate of 2. So I know the rate of change of h with respect to t is positive 2. What do I want? How fast is the volume changing? So the volume is big V. And I want to know that when R is 1 and H is 3. Read the problem very carefully. I drew a picture of the situation. I write down what do I know, what do I want to find. The fourth step is to come up with an equation here. Remember how to find the volume of a right cylinder?
Pi r squared h.
Pi r squared h. So by tomorrow you should look up some of the common geometry formulas. So you should know something like that. And so now, step 5, we're going to differentiate implicitly with respect to time. Which means differentiating v, I would get
V prime.
v prime, or let's specify dv dt. How do you differentiate this?
Pi 2r dr dt dh dt.
2 pi r dr dt. That's me differentiating the r squared function times h plus pi r squared dh dt. I just apply the product rule because I have a product of 2 functions here. I have r, which is a function of t, and I have h, which is another function of t. These two are multiplying, so product rule applies. Differentiate r squared, that's 2r, r prime. Differentiate the h, that's just h prime. And so now I have a relationship with the rates involved. So now what I want, this is the guy I want, dv dt. And so now to check, do I know everyone else? Well, yes, I know dr dt is 1, I know dh dt is 2, I know r is 1 and h is 3, so I'm just going to plug these guys in. So that is step 6. Plug in. So I know my dv dt here is going to be, I don't know if I'll have enough space here, 2 pi times r, which is 1, dr dt, which is also 1, times h, which is 3, plus pi times r squared, r is 1, times dh dt, which is 2. So I end up with 6 pi plus 2 pi. So the rate of change of that is 8 pi, and this would be meter cubed per second. Okay, but 8 pi. Don't necessarily care about the units, it's not a physics class. But that would be your answer. The volume will be increasing by 8 pi. So go over this example again, we'll do a few more from this, so bring these tomorrow. We'll do a few more examples before moving on. That's basically related rates. Oh, I also do have your tests to give back, so let me do those now.